Good afternoon, everybody. Let me welcome you to next of our reinforcement learning lecture. It can happen that this week it will actually start going to be slightly deep, so we will see. The slides I have there before the presentation itself, they are usually cover more topics than I will be able to deal with on the lecture, because we have the longer lecture, so I never know how much exactly of the things I will cover. So don't worry if it seems like that it's a lot. I will trim it down after seeing how far we have actually got through the lecture itself. So before I will start, are there any questions or something you would like to ask or tell? The first assignments will be due tomorrow, right? So there's also a consultation tomorrow if you have any trouble. And of course, we have Piazza. So we ended the previous lecture with a temporal difference algorithm, one which can learn even during the episode, right? By estimating the overall return by doing like a single step, which gives you one reward, and then you say, okay, and the rest of the episode, well, we will just estimate it based on the value function or action value function which we currently have. So the update of the SARSA algorithm generated state, action, reward, next state, next action, right? And then we say, okay, so the idea of a return in this step will be obtained or can be estimated this by taking this one step reward, right? And then if we have not finished, then gamma times the value function in the next state. But we don't have the value function in the SARSA algorithm. So again, we estimated this by sampling an action, right? From definition, this value function is an expectation over actions from the policy, right? And here is the action value function as t plus 1a, right? So we have just taken one of these actions, sampled according to the policy, and that was it. And we also discussed a Q-learning algorithm on the practicals, which differed in a way that here, instead of sampling the action from the policy, we have just said, okay, let's just imagine the best action which we could do in the next state, independent on what our policy is. And we saw that when we discussed the epsilon greedy during training, right, the advantage was that while the SARSA incorporated this epsilon greedy behavior to the optimum, to the solution, so it found a path which tried to avoid the cliff because, well, that's what it saw during training. There was a chance that you could just close your eyes and fall off the cliff. The Q-learning was able to find the optimum behavior independently on the exploration which we did. And so this difference between these two algorithms is actually very fundamental, and we will talk about it for a bit now. So until today, most of the methods which we described were so-called on policy. We'll be using that term, and what it means is that the same policy was used for both the generating the episodes and the target value, the target policy of the value function. So the thing which we wanted to obtain was from the same distribution as what we used to generate the data. And that's what on policy is, and off policy is the difference, right? So sometimes, or most of the times actually, generating the episodes needs to contain some amount of exploration so that we can actually get to find the optimum solution, while the target policy, the one which we want to learn or to obtain, should probably not include the exploration just for the sake of itself. Instead, it should be the optimum policy with respect to the original environment. So it makes sense to talk about two policies. So we will mostly discuss two policies. The one will be the so-called behavior policy. It has a new letter, that is B, and that's the policy which we will use to generate the behavior. Right? So whenever we generate the episode, we can generate it from the behavior policy. And then the target policy, which is still pi as before, will be the policy which is being trained or learned. And usually the difference will be in the amount of exploration. But it also can be a question of like time lapse, in a sense that in the future, what we will do is we will train in a distributed way. So we will generate data by having several computers, and each will generate the episode. And then once the episode is generated, it might be sent to some master learner. And when it happens, then there also be two policies, right? The current, the updated one policy, which the master learner has, and then the episode which we have generated, but that was generated with some older version of the policy. So then again, the behavior policy used to generate the data will be different to the target policy because of the time difference, right? Like the target policy has been updated already, while the one which was used to generate the behavior was older, so they are different. And in the off policy settings, we will consider these two policies to be different. Right? They, of course, can be the same, and then we are in the on-policy setting. So the off-policy methods have several advantages. What it means is that we can use more exploration during generation or when generating the episodes or interactions, while our target policy might be non-stochastic. And also it means that we can handle data which might not be generated by us. Right? It might even happen that, I don't know, you want to learn how to fly an airplane, and you can get a glimpse of some human operators which are actually able to do it. So you might see what good trajectories are, what good episodes are, but they are generated by usually unknown policy to you, right? Somebody just did it, right? But we are using the policies in various places. So in order to use it, we need to be able to use this off-policy kind of setting, and ideally one where the behavior policy is even not known, right? On the other hand, the off-policy methods are usually more involved. We need to deal with the fact that we have generated the experience differently than what our target policy is, and because usually they also converge in a slower way. But many of the algorithms we will describe will be of this kind. We'll be using this on-policy and off-policy distinction for the whole lecture because it's one of the major differences between the algorithms which there is. So we will start today to discuss some straightforward, it may be difficult to say straightforward, but relatively simple approaches how to enable off-policy learning. So let's do that. And let's say that we have got two policies. We have got the behavior policy and the target policy. And what we would like to do is we would like right now to use trajectories generated by the behavior policy to just estimate the values for the target policy, right? So we want to compute let's say, the value function of the target policy. And here there will be expectations which will sample the actions from the policy, right? That's what the value function does. It tells you how good you will be on average if you'll follow the target policy pi. But instead, we will have sequences where the actions are sampled from the behavior policy, right? So we cannot use them in a straightforward way to estimate these expectations because, well, the actions don't follow the same distributions. But we will see a way of how we can do it. It's not straightforward. So if we should have a chance of succeeding, what needs to be true is that if the target policy is willing to take some action in some state, the behavior policy must be able to do it as well. Like if this didn't hold, if the target policy was willing to take an action and the behavior not, then we would never see the action taken in that state, and we could never estimate the expected return because, well, hic sunt leones, everything could happen, right? It could be the optimum behavior, but we don't know because we will never see it. So we will always want the target policy to be covered by the behavior policy. And so if this is true, then the one very frequently used approach how to deal with off-policy training is to use so-called important sampling. Important sampling is not really reinforcement learning only thing. It's a general method for estimating expected values with one distribution when you have samples from another distribution. And that's the situation we are in. We have sampled the actions from the behavior policy, but we want to estimate expectations of the target policy. Right? So now I've stopped using the reinforcement learning notation for now to show you that this is a general concept. So let's say that we have got two distributions and we have sampled from the first one. So we have got xi and samples from the first one. They are independent. And we can estimate some expectation from the first distribution, well, just by averaging the samples, right? The average of these samples, that's an unbiased estimate of the real expectation, right? Even just one of these, even just one fxi is an unbiased estimate of that if the xi is generated from the distribution P. An average is also an unbiased estimate, but it has lower variance. It's a better estimate. But now, let's go the other way. Let's try to estimate the expectation where the x's are generated from the other distribution, so from Q. So that we want to do, and what we will use is we will use the following fact. If you consider the expectation where x goes over q, then you can rewrite the expectation where we will be sampling from p. It is actually trivial to realize how it works because here I'm not going for the integrals. I'm just going for the sum. Right? We go over x's and we have got qx times fx. And then what we want instead is to rewrite it so that we have a weighted sum over px, because that will correspond to the expectation where we sample from p. So what we need to do, well, we need to put qx there, and we need to divide by px, right, in order to these things to cancel. And then here we will still have fx. Oops. So, but this, even if it's a trivial trick, it's something what allows us to change the distribution from which we will sample. We are dividing here by px, so it needs to be non-zero, but that's exactly the thing which we discussed here, right? For this to work, if x can be generated by q and we need to include it in our expectation, it needs to be also generated by p, because otherwise we have no chance of actually doing the expectation. So we can estimate the expectation from the other distribution by taking the average, but each multiplied by so-called relative probability of an outcome in these two distributions, right? So this says, okay, if this outcome x, for example, action, is 2 times more likely in the distribution Q, then it will play twice the size of the role in the final output. Yes?
I have a question. Isn't that kind of similar to higher convergence?
Yep. So it's true that this kind of ratio is also present in the KL divergence. But as you said, the logarithm is missing, and on the other hand, this part is here. So I don't know how to use it explicitly, but definitely at least the ratio is. And if we did if we at some point did the logarithm of that, it could be there somehow. But you are right in a sense that in some later theorems, we will actually create an KL divergence out of that. It's not really visible right now, but if you imagine that you are computing the logarithm of some expectation, then there is a Jensen's inequality, which tells you that this is and either larger or equal or smaller to equal. I would have to think what exactly we have there. But one of these inequalities holds, and then you can put the logarithm inside. Right? So you can swap expectation and logarithm, but it's not an equality. It's just an inequality, but it is inequality in one direction. And that way, we will get the logarithm of that, and it will be a KL divergence. And we will see that because it's non-negative, it will help us. So there will be situations where this will be used, but the origin of this ratio is kind of different. Like we really wanted to get the two estimations, so we had the ratio there, but because it's there, we will be able to play some tricks with it. Yes, I kind of think that it is. There are various algorithms for sampling from one distribution and the other, and there is also rejection sampling and things like that. So yes, all of that is based on the same idea that you are sampling one and then trying to estimate what would happen from the other distribution. Yep. So, by the way, both the estimates, even the one including the relative probability, are unbiased, but the variance can be quite high because of this ratio, and we will see some practical examples. So now, where are we going to use important sampling? So imagine that we have generated an episode, or we have some initial state. So the probability under some policy pi, well, that means the agent needs to choose an action AK, and then the environment needs will produce the next state, and we will multiply this for as many time steps as required. So the relative probability of two trajectories, right? When we have one episode and then another episode. How does it look like? Well, because it's the same environment in all steps, this goes away. So the relative probability of the whole trajectory is just the product of the relative probabilities of choosing the individual actions, either from the policy pi or from the policy p. And this is the notation which we will use. So the rho t is the relative probability of two trajectories were starting in time step t and then continuing until the end. And it's usually called importance sampling ratio. it is also the relative probability, but when I say importance sampling ratio, then this is the ratio which will now appear in our formulas. So generally, when we want to estimate the value function of a target policy, and we have generated an episode from the behavior policy, and we have obtained a return, right? We can make it, or we can make it the value function of our target policy by including the importance sampling ratio here, because by doing that, it will change the expectation so that instead of sampling the actions from B, it will numerically be the same as if we have generated the actions with the target policy. But when you look at it like that, the overall effect is that, well, when I want to do the estimation for the target policy, which is different from the behavior policy, we just need to multiply every return by this importance sampling ratio. If the two policies would be the same, this would be 1. So that's the setting in which we are in. But if they are not the same, then we can still use the data from the behavior policy to give us an unbiased estimate of the target policy. So normally, what we do is we estimate a value function by computing an average. Right? We are usually we are observing multiple returns from one state, and we average them all, and this will converge to the real value, right? Because we'll see more and more numbers, and by the law of large numbers, that will converge to the real expectation. And we can do the same thing here. So if we have observed some number of returns for the state S, but they were generated by the behavior policy, then we can estimate the value function for the target policy by, multiplying each return by its importance sampling ratio and summing, and then dividing by the number of times when we have visited S. So this is just an average. But there is, of course, a reason why I'm writing it so complicated here. So this is called ordinary importance sampling, and it's unbiased, but it has very large variance. There are even environments where this has infinite variance. So independently on how many samples you'll do, this will have an arbitrarily large error after any number of steps, which is bad, right? So we will normally use a slight modification of that, which is called weighted importance sampling. So what weighted importance sampling does is that we average these observed returns, but we understand or interpret the importance sampling ratio as weights, and we do the weighted average of these G's, right? So the difference is that just in this denominator, where here we sum the seen importance sampling ratios, while in the above we have there just the number of times where we have seen that. So this thing is biased, unfortunately, but it is consistent in a sense that it at least converges to the correct solution, but it has much smaller variance. So to see why this is unbiased, if you imagine the importance sampling ratio, I will create probably a page for it. Then what it is, well, it's an, it is like for some action, it's the behavior, I don't know, sorry, the probability of taking A from the behavior policy divided by the probability of taking A from this policy. So I could have written it much simpler, right? A given S, and here I would have this thing. And so what I want to say, the problem with the book which we are using is that a lot of things are just being stated, so I will try to convince you mathematically here that they are true, and I may be stumbling a bit, but hopefully I will make this. So what I want to say, or to convince you that the expectation of this important sampling ratio when we compute the expectation with respect to the target policy, so that this thing is 1. So if it's relative probability, then on average it will be 1 because we have got 2 distributions. So why this is the case? Well, it's kind of straightforward because this is just the sum over all the possible actions taken from the target policy, right? And now we have the important sampling ratios here, and you can see that the target policies will cancel. So this is just the sum over all probabilities from the behavior policy, and well, that's 1 because it's a distribution, right? So this thing, because they are samples of the important sampling ratio, by the law of large numbers, this converges to the number of times which we have seen as. Right? So it might be off at the beginning, but once we will see many of them, because on average this ratio is 1, then the sum on average will be the size of the set, which is this thing, so it will converge there. Now, this is definitely not a mathematical proof because you would need to think about the variances and what exactly dividing by that does, but it's just like a view of why that should be the case, right? In the end, we are doing the average, but at the beginning, it might be different. So what is the difference between these two methods? So consider the original multi-armed bandit case or example, which we have seen all, and let's have a look at what will happen when we will do some computation. So let's say that our behavior policy is to uniformly choose any arm, right? Any action. That's a good exploratory policy. It tries everything. And now let's say that our target policy is always choose an action 3. And so generally, what we are saying is that we can estimate the value function of the target policy. So we can see what, on average, this policy always use 3 does. And this can be computed by seeing somebody play all the arms, so using all the arms. That doesn't, that's not unreliable. It kind of makes sense. Like you would just consider the episodes or the steps where the behavior policy actually uses this action 3, right? And then you'll ignore all the other ones. So in the ordinary importance sampling, what we do is we take the reward and then multiply it by the importance sampling ratio. So first, if a different action than 3 is chosen, then this action is 0 probability under the target policy, so we get 0. That's kind of fine. If the player chose a different action than 3, we don't care what they got because that does not belong to the value of the target policy. On the other hand, if an action 3 is chosen, then how does it look? Well, the action 3 is chosen with 100% probability from the target distribution, but in the behavior policy, it only gets 1 over 10. Right? So the importance sampling ratio is 10, which means just that the action 3 is 10 times more probable in the target policy than in the behavior policy. And so whenever we will see a reward from the action 3, then we will add 10 times as much to our estimate. And the thing is, if we will do this and we will average things by sampling from the behavior policy, then in 90% of cases, we will get nothing, and in 10% of cases, we will get this, which is 10 times as much, so these 10s will cancel out, and on average, we will get R. But the problematic part is this 10, right? Imagine that after the first action, After the first action, the behavior policy magically generated 3. So our estimate will be 10 times as large as the real value. It is important for it to be unbiased, but it's obviously wrong. If you imagine that this R would be like the percentage with which you win or something, then you will say, it's 10 times as much. I will win with 1,000% probability or something, which it doesn't make sense to say 10 times as large value. It needs to be there for the unbiasedness, but as an estimate is awful. And so the weighted importance sampling, what it does is that it divides this by 10, right? Because it just does the weighted averaging of various rewards. So there will be, instead of dividing by 1, we will divide it by 10, and we will get R. Now that's much more sane, right? We have seen one sample from the action 3, and we say, this is it. That's the estimate, right? That's not bad. After seeing just one estimate, that's probably the good thing to do, even if this is actually biased, because on average, you are estimating too little. So we have an example here on some more advanced environment. So if you remember, we talked about blackjack, where our goal was to draw cards until we say stop. And then the dealer did that as well, and whoever got closer to 21 won, unless the other player got over. So let's say that we would like to do the evaluation in the off-policy settings. So let's say that we have got some fixed state. So the dealer is showing you, so they have a card with a value of 10, which means they are in a good chance. And we are seeing some specific situation. So we have got 13 with the usable ace. And so in this situation to win, we would need to get either 20 or 21 probably, because if the dealer is showing good use, there is a good chance they will get 20 as well. And in any case, let's have a target policy, right? It's fixed one, and we will generate episodes again by using the behavior policy, and we will use the ordinary importance sampling and the weighted importance sampling to give us the estimate of the value function in our target policy in that one specific state. And so here we can see the number of episodes which we will do, and here is the error of what the estimate of our value function is compared to the real one. And you can see that the ordinary importance sampling starts with a dramatic large difference, which nevertheless converges to the real value. So after, 1,000 episodes, it seems fine. The weighted importance sampling starts with much lower error, but converges to the same thing, even if it is biased when you consider just fixed number of episodes. Like it's consistent, so if you consider more and more episodes, both of these lines, they should always get to the same place. But if you look at some fixed budget, and you would look at the average values generated, then the weighted importance sampling is biased, then it will underestimate the real value. But what's the whole point in this is that we will almost universally use the weighted importance sampling thing because it converges to the right solution, but it has much smaller variance at the beginning. Even if mathematically we could have gone for an unbiased estimator, but yeah, it would suck. So how to do that? So let's start by doing off-policy Monte Carlo evaluation. So we are just doing evaluation. So let's say that we have some target policy and some behavior policy, and we just want to estimate the value function for the target policy by having samples from the behavior policy. So what we need to do is the following. So we have this VPy, and that's So what I'm now doing is that with Monte Carlo, we had this nice incremental solution where we had the estimates from the previous step, and we were able to update them to the new estimates and how it looked like. Well, we had these Q values, right, which were the averages. So I will say it correctly. Qn plus 1 is n averages of Ri, R from 1 to n, yep, something like that. And we knew that this could be computed by taking the previous step and then 1 over n, and here was Rn minus Qn. So now we need to do the same thing, but we are in the situation where our Qn plus 1 is not just an average, but it's a weighted combination of the returns. And so when we do it, we will get to the formula which is there in the slides already. So let's do that. It should be hopefully easy. So what we need to do is we need to create the Qn there, right? So the Qn, what it is, well, that's this sum, but going from n to n minus 1. Then we have got this one and this one. So then we have Wn Rn, right? So I have just separated the thing in the denominator in the two things. And now, as you can see me, I'm doing it here without trying it by myself first, so we will see what will happen. So let's make this a bit smaller. Oops, sorry. I should probably do it on the touchpad, that's much safer. So, we want to create the Qn from here, so we will say, okay, let's consider Qn. But what we need to do is, well, we needed to divide it by the correct denominator, right? So we can imagine that we will add it there, so there will be sum from I to 1 to n minus 1 of the Wi times Qn, right? Because we needed it in the denominator for this to be Qn, so we have added it there, and then we will have Wn Rn divided by the overall sum. So what we will do is we will keep something which are the counts, right? We had the counts previously, that was the n. How many times we have already seen this specific, so how many numbers we have in our estimate. So now we'll have a different quantity, and that will be the sum of the weights which we have accumulated for this state action pair, right? So this quantity, this sum of all the weights hidden in the Qn, that's what the Cn will be. So this is the sum of these weights. And if we have this quantity, then how does this look like? Well, this is Cn times Qn plus Wn Rn, and it's divided by the Cn plus Wn. So this is what we can use. And so how will our algorithm look like? Yeah, I think it will be fine to do it. So yeah, maybe one more step to make it completely obvious. So we can rewrite this by getting rid of this Cn here. So you can imagine that this would be a full Qn minus Wn Qn. Yep. Right, because to have a whole Qn, we would need Cn plus Wn. We are missing Wn there, so we can imagine that we put it there and get a whole Qn, and then we need to give it back, so that will be minus Wn times the Qn. Is it fine? I don't know if I'm too quick or not. I'm kind of feeling that I've lost you. It was too detailed, maybe. Okay, so, but I kind of believe that this is all fine. And then the remaining update is that we will take the Q, right, this part, and then we will do an update where we'll have a difference between the return and the Q, right, which is this thing and Rn here, even if it's G there, right? And it's all multiplied by Wn, right? That's W in these settings, and divided by the count of all the weights which we have seen, right? So the overall point is that we can quite straightforwardly update our formulas for doing the incremental update of the values. The only difference is that here previously we did +1, so it were counts, and now it will be the sum of weights of the samples which we have got. And then here, instead of 1 over count, which was before, it's W divided by the sum of all the weights. So we get a very analog thing, and you can easily see how it will be the same as the previous algorithms if all the weights would be 1, which is exactly if the target policy and the behavior policy would always be the same. Yep. So the importance sampling ratio here, that's the, like, we are computing the row, right? So we are going from the end of the episode, and in every time step, we multiply it by the importance sampling ratio of that one specific action, right? Well, because if you have the whole episode, then if you are in timestamp t, then this row t is the product of all the, I don't know, I is from t to the end of the episode or something, right, of the generating the action AI. Sorry, the other way around. Right, something like this. So what we do is we compute it from the end. Right, so in every timestamp we add one more factor, which means we multiply it by the relative probability of the action in the current timestamp. So we can then easily update it into an algorithm which does the full policy iteration. So instead of just evaluation, we'll also do policy improvement. Like that's what we do. We estimate the policy, and then we use the estimates to get a better policy. So usually we just use the epsilon. The greedy policy, and especially for the target policy, we care about the greedy policy only, right? So we can do the updates immediately and then just update all the estimates. So some algorithms are technical in a sense that they require this importance sampling ratio fiddling so that you can obtain the results which you need. And it will always be technical to make sure that the values are there correctly. But surprisingly, we will see algorithms which are quite straightforward, even if they are actually off-policy algorithms. So to see such an algorithm, let's consider a modification of SARSA, which is called expected SARSA. So in SARSA, what we do is we estimate this expectation by sampling AT+1 from the policy and then looking at what QST+1 A+1 does. But what we could have done instead is, well, we could compute the whole expectation, really not estimating it, but if we only have some limited number of actions, for example, when the actions are discrete, we could compute this exactly, right? We could consider all possible actions from the target policy and just use them. And if we have done it, well, one thing is that we have removed one source of the variance, so it will probably be better than the regular SARSA. And we traded it for, I don't know, maybe a slight increase in the number of actions, but that's usually negligible. But the important thing is that this algorithm is actually also an off-policy algorithm. Because even if we generate the actions from the behavior policy, then the only place where in the algorithm we need to choose action is here. Right? This is the only place where the behavior policy was, right? Because in the trajectories, the actions were generated by the behavior policy, but we want the expectation from the target policy. But if we compute it exactly, if we do this, then there is no other place where we would require the actions to come from the target policy. So it's perfectly fine if they are generated from the behavior policy. Right? So we have gotten an off-policy algorithm for free in a sense that all these important sampling ratios are just not present. And when you consider Q-learning, then actually Q-learning is a special case of this expected SARSA, right? So in Q-learning, what is the target policy? Well, the target policy, that's just the greedy policy with respect to our estimates. So the target policy gives you such, or as, such an A that Q as A is the largest. Right? So if you consider that your target policy will be always greedy with respect to your estimates, then here what you would get, well, you would consider all the actions, but only one has non-zero probability, right? The one which has the largest action value estimate. So this quantity is in fact the maximum of QSA which we can see, right? Because if you consider the action which gives the largest action value estimate and then compute the action value estimate of that action, well, that's the largest value which there is, right? So the Q-learning is actually an it's an expected SARSA with the target policy as the greedy policy, and it's also an off-policy algorithm. We have actually, intuitively seen that in the cliff example, right? Because we saw that the Q-learning was actually able to generate the optimum policy, even if the behavior policy was the epsilon greedy one, right? So we have discussed that as an important difference between the Q-learning and the SARSA algorithm, but that was caused by the fact that the Q-learning is in fact an off-policy algorithm, while SARSA is not. So the SARSA is incorporating the behavior policy into the optimum which it tries to achieve. So, in this graph, the authors of the book just want to show that there is a difference between the expected SARSA and the SARSA algorithm. So, if you can, you probably always want to go for expected SARSA because, well, why not? Unless there is really a large number of actions. So, some algorithms are much easier to work with in the of policy setting, but yeah, it's a topic which we will keep with us for most of the course. So we will see some off-policy and on-policy algorithms in the future as well. So let's put that aside for a bit. It seems like that the Q-learning is a nice algorithm. It's kind of simple. It's of policy, so we can use any data to run it on. So let's discuss one of its shortcomings. The Q-learning has one problematic part being, the algorithm itself has one weakness. That's a better word. So let's have a look at what it is. So let's say that we always start with an episode in the state A, and we can decide to go either left or right. So when we go right, we get a 0. And when we go left, then there will be many possible actions. And in each, we will have a reward, which is on average negative, right, minus 0.1, but with some non-trivial variance. So when we go to the left, sometimes it will seem like that we get something positive, sometimes it will seem like we get something negative, but on the average, the negatives are slightly stronger. Right? So the optimum behaviors go to the right because on left, on average, we will just lose. And so let's have a look at how the Q-learning will progress. Well, when we run Q-learning, then we can see that at the beginning, it will start doing many actions to the left, to the case where most of the actions which it does will go to the left when measured over an episode, and it will take quite a long time for it to realize that it was a bad idea. So why does this happen? Well, this happens, or this name of the phenomenon is called maximization bias. And the problem is that when we get to B, and we want to say what is the expected value function in this state, well, what we do is we say, well, we will consider any possible action, and we will just have a look at what that action will give us from this state. So if you imagine that there are many actions, then some of them will get positive output, some of them will get a negative output. But in Q-learning, you always say the value function of this state with just the maximum of all the possible returns which we would get when choosing the action. So if only one of these estimates is positive and all the others are negative, we will overestimate how good it is because we will just always take the largest quantity, right? So at the beginning, there probably will be some of the rewards there which will be positive, and that's why the algorithm will choose to go to the left. Because at least one of these actions still seems to be hopeful. We will get rid of the phenomenon or the effect by, well, sampling each of these actions so many times that the average will get below 0 for all of them, but it will take time. And the problem is that we are using the maximum to give us the estimate of the value function, even if the average would obviously be smaller. But the maximum is built in there because we want the greedy policy, which we want for all other reasons. So it's not as simple as saying, well, then just get rid of the maximum, let's do something else. But what we cannot, because the greedy policy is still the good thing, right? We want to find a policy which maximizes the expected number of returns, the expected return. But in the algorithm, it's making a kind of a problem. Luckily, people have come up with a way of how to balance this problem with an approach which is called double Q-learning. We will see it not just today, but also in the future. Many of the algorithms suffer from the maximization bias. So even if I'm illustrating it on Q-learning right now, it will actually be present in several algorithms in the future, which is why I'm taking my time to talk about it. So a way how we could improve the behavior is the following. So where does this maximum comes from in the Q-learning? So in the Q-learning algorithm, when we update the Q, we say, okay, the Q is Q minus learning rate, and now here we have the reward plus gamma times the maximum over the actions of the Q as, I don't know, I should say S prime A minus Q, right? So we care about this part. So this, how it actually works, well, first we can look at it like this. We take an action which would maximize the QSA, right? And then we really take the value. So you can look at it that we are doing two steps. We are choosing a greedy action, and then we are computing or getting the expectation for its return. And the problematic part is that we are using the same estimate for both of these. Because if we use this Q to get us the best A, and then we evaluate this action using the same Q, well, the result will be, it's great. It's great. That's how it was selected, right? If instead of this Q, right, we could say, okay, so let's really get the unbiased estimate. If we had another way of estimating that, then the maximization bias could go away, right? Because even if in our first estimate this action looks great, if we considered an independent estimate of that action, it would not necessarily be great. It might be less for 0 or above for 0, and on average it would be slightly less than 0. But if we use the Qs for both, then that expectation, like when we do the evaluation, it will always get us a good thing. So one way how to improve the Q-learning is to untangle these two Q value functions. So what we will do is we will train two action value estimates. That's why it's called double Q-learning, and it will be Q1 and Q2. And when we do the update, then we will choose an action which is best according to Q1, but then we will evaluate it by using the other estimate, Q2. And if they are uncorrelated, then the maximization will go away, because even if we take the action which is best according to Q1, it should be like meh according to Q2. But of course, now when we have two estimates, we need to update both of them. So what we do usually is we just randomly improve either Q1 or Q2, and then when we generate an action, we can either use Q1 or Q2 or their average, whatever. All of them should theoretically work fine. The price is we need to do like twice as many steps in a sense that we are updating two Q-value estimates. But what we get is the less pronounced maximization bias. So here you can see that when a double Q-learning is being used, it will actually start converging to taking the right action without going to the face like, oh, left is great, let's go left. There is this one action out of 1,000 which is the best, right? Because, well, even if one action randomly or gets a larger quantity in Q1, the chance that it will also happen in Q2 is much smaller. So we will not have a systematic push to go to the left side. Yes?
Can you go back to the algorithm? Why are we not updating both VQ at the same time? Updating either of them.
Yep. So the question is why we are updating only one of them. We could update both of them at the same time. So if we really used both of them from the beginning, then they would always have the same value. But for this maximization bias prevention to work, we need the Q1 and Q2 to be uncorrelated. Like they need to be different enough so that they give us independent estimates in what's going on. If they started with the same value and we did the same set of updates, then they would always be the same. But what we could do is, for example, update Q1 all the time and then update Q2 only half of the times. That would still give us more updates, but hopefully the effect could be less correlated. But the idea of doing them completely independently is the belief or the hope that they will be independent enough because in different estimates or different really transitions are being used to train them. So we could do some trade-offing and we could train them more frequently for the cost of them being more similar. But usually the simplest formulation is to train each of them independently.
Is it possible that both of the queues tend to generate different kind of actions, so that one might be so that they explore different corners of the environment, so that they may be very imprecise. One may be very imprecise where the other one tends to choose the actions.
Yeah, so when we have these two actions, two estimates, it might happen that one of them is very bad, right, and the other is kind of better. So, I don't know, choosing from both of them might not be great, or
one may not explore the same corners of the environment as the other one. So one might be bad in some very specific thing that the other one chooses to do.
Yeah, so it can definitely happen, and it probably will, that they differ in a sense that one of these estimates will say, like, going to the left is a good idea, and the other could say going to the left is a bad idea. So they could, like, guide the exploration in different directions. Then that definitely can be the case, but they should converge to the same thing, ideally, because they both will converge to the optimum policy. So in the end, we hope that they should be the same, but the fact that they are different at the beginning is what we hope will actually help us with the maximization bias. So I'm not really sure if I answered the question anyway, but yeah, let's take it offline. Yep. Okay, so what we have seen. We have seen on policy and off policy. I have bored you with the importance sampling ratio kind of way of how to make a Monte Carlo into an off-policy algorithm. We have seen that expected SARSA and the Q-learning are actually off-policy algorithms which are very straightforward and thus kind of useful. And now we will deal with one more step before we start talking about neural networks. And this one more thing which I want to discuss are the n-step methods. So we are in a situation where we have either temporal different methods, which says, okay, I will estimate the whole return by doing one step, and then looking at the value function which I have to give me an estimate of the rest of the episode. And then I have Monte Carlo-like algorithms which start in the initial state and then simulate the episode until it ends. So it seems we could do something in between, right? In theory, we could say, okay, let's get an estimate by doing some number of steps, and then looking at the value estimate, so we will just estimate the remaining of the episode by just looking up some table or model how good it is. And this middle ground in something which is something which is called n-step methods. So n-step, because when we are estimating the return, we will do it using n steps of where we really get n times reward or n rewards back from the interaction, and then we will just take the value function estimate from the state where we got after taking the n actions. Here, if the episode ends before these n steps, then I will just use the usual boring sum of rewards kind of thing. So this is a so-called n-step return. And this notation from t to t plus n means that we are using explicit rewards which we got after doing n actions, so from time step t to t plus n. And then we will estimate the return from the final state by looking at some estimate of a value function. So this actually encompasses both of the algorithms which we have seen. Like if n is 1, this is temporal difference method. We will do just one step and then compute the estimate. If n is infinity, then this is Monte Carlo, right? We will just do infinity many steps, and then we will estimate the rest of the episode from our estimate, right, which will never happen. But we can go somewhere in between, right? So instead of doing just one step in the temporal difference methods, we could say, okay, let's do 10 steps. That will give me a much better idea of how good the first action is. And then the estimate of the remaining of the return will play less role on the result because, well, especially if you are using discounting, it's fine in the future, so it's just a small volume which it will influence the final outcome with. So when we do the updating, it's still the same, right? What changed is that we just use this n-step return here in the update place of the algorithm. But other than that, everything can be the same as it was before. So that's nice. The algorithms, at least on the slides, will become slightly more complex because we can do this update only after we have actually performed n steps, right? Because that's the only time where we have where we can compute the n-step return. Right? So if you imagine that we want to do, I don't know, 3-step return, you need to do the 3 steps before you'll be able to do the update of the value function in the first state, right? So when you do it, then whenever you would get this, you would update this value function, and then after doing one more step, you will update this value function. So there is this delay between when you generate the data and then when you are able to really update the estimate for the given state. So the algorithms are slightly tricky. And also at the end, right, when you know that there is no more action, you still have several estimates to do, like this one, and this one, which we couldn't do before, but now we can because, well, we know that the episode ends. So on the slides, what the algorithms do is they have got like t, that's the current step which we are doing, But and then we have the end of the episode, right? So until the episode has ended, it's fine. We'll just do the usual stuff of collecting more data, so generating connection and taking it there. And then we will consider the state which we have seen n steps before, right? The tau thing. And now if this is larger than 0, it means, okay, if we have done at least n steps, we have some update to do. We will sum these n steps which we now know that we have actually encountered, and we'll do the update. And then this loop will go even after the episode has ended, right? Because we need still to process the end of the episode. So we will go physically through this loop some more times. We will not generate any more observations, but we will do the final updates. And then when we have really updated the last step, which means that the small t is something like tau plus n, then we will stop, right? It's a bit technical, but apart from that, it's nothing very difficult about it. Whenever we can actually compute this n-step return, then at that time, we will do the update. So to see the effect of that, let's consider some random walk example. Well, because the Monte Carlo is naturally bad in these stochastic environments, but the authors say that it's like a random walk. You start in the middle, but we will have 19 states instead of 5. And we could train an algorithm. So we could train an estimate, and here what we are seeing are the errors in the estimates, and there are different n-step methods being used. So this would be the temporal difference where n is 1. Then here is n 512, so that's similar to Monte Carlo. And you can see that the optimum is really somewhere in the middle, in a sense that they use the 4-step method. Of course, the 4 depend on the number of episodes which we are doing, right? If you would be doing infinite number of steps, then you would probably want to go for some larger n, because the variance of that is smaller. So for them, 4 is good because they just consider small number of episodes at the beginning. But so it's problem dependent, but it makes sense that the optimal value is somewhere in between, right? To do some mix between the one-step methods and the Monte Carlo methods. Questions? Nope. So the remaining he is straightforward. So we can do an n-step SARSA, right? We just did the value estimation, so now we are also trying to update our policy. And so the n-step return, it's, well, the n steps, so n rewards, and then we will do the value estimate in the next state, and in a SARSA, we do the value estimate by also sampling connection in that state, right? So that's really just the same thing. So what does this mean? So we had this one environment where we went through some grid, and when you actually find the way to get to the goal, what you will do is you will say, okay, so I can actually get something. So imagine that when you get to the goal, you get a plus 100 return, right? Reward, sorry. So if you do that, then the TD estimate, it will update only this one state, because that's the one from which we got to the goal. And then it will say, yeah, it has stopped, so now it's over. And it would start again, right? So that seems weird, right? But in the n-step method, what you will do is you will, if it is a 10-step method, you will consider all the 10 steps before you actually reach the goal, because for all of them, you will see the 10 rewards, including the final one of plus 100, right? So what you get is you spread the information much more quickly, not just across one time step, but across n time steps, so that's a positive thing. The downside, you know, everywhere there has to be a downside, is that at the beginning you cannot start after doing the first step, but only after you have performed n steps, you can start doing the updates. Right? So n equals to infinity, that's Monte Carlo, might not be good if we cannot actually solve the episode by ourselves, but going for n10 seems that it should work, right? Because even if for the first 10 steps we get no updates, we will start doing the updates afterwards, so if we cannot solve it, we will still learn online. But once we have found a way how to solve the problem, we will remember this information in many more states than just in one. So, so we can write it as an algorithm, again, slightly tricky one, but apart from do this update whenever you have all the values which are there, there is nothing logically complicated about it, it's just technical. Don't worry, you will have your chance of implementing it in the assignments. So I will just skip over that because you will have a chance in the future to really implement it. But don't worry, it's simple once you think about it. And now we get to the part where we will combine the off policy training and n-step methods, right? That's the last thing which we will do before going for the models. So, we know that when doing the off-policy training, we are interested in this, with these relative probabilities of an action being taken by the target policy and the behavior policy. We previously used this rho t, which was the importance sampling ratio from the time step t until the end of the episode. So now what we will do is we will deal, like now how our estimates will look like, well, we'll be in some state, we will do some number of actions, and then we will take the rest of the quantities from the value function. So the value function will be the one corresponding to the target policy. So we will not need to handle the mismatch. We'll only need to handle the mismatch between the behavior and the target policies in the actions which we have done in the n steps, right? So for that, we will need importance sampling ratio, which covers actions from t to t plus n, right? If the episode ends sooner, we'll do it correctly. But generally, this means, okay, deal with the actions between t and t plus n. So if we did the evaluation, if we just perform the updates of the value function, then here we have got n actions. So here we have generated actions from at to a t plus n minus 1 from the behavior policy, but we want the updates to be in the target policy, so we need to deal with these actions. So we need to include the importance sampling ratio from the time step t to t plus n minus 1. Like n numbers need to be there because we have selected n actions. Now, let's consider n-step SARSA. So in n-step SARSA, we are in the situation that we have got ST. We even have AT. The AT, the action T, has been selected already. It's not a part of the value estimate. It is given to us, so we don't need to deal with it. So one difference here is that we don't need to take care, we don't need to handle the action AT. On the other hand, we need to take care of action AT plus N, because the action AT plus N is being used in this estimate of the return to tell us what the value function in the ST plus N looks like, right? If I'll go back, here you can see that in n-step SARSA, we also need the action in the state T plus N, ST plus N, because that's what we do to give us the estimate in the state ST plus N. So we have increased both of these, right? So this has increased and this has increased. So why are these plus or minus ones important? Yes?
So if we do the SARSA with the policy, then we do actually sample the AT from the like behavioral policy and not from the policy.
Yes. That's like how we do it always. In a sense, like when we generate it, we always generate AT from the behavior policy, even the one which we use here to do the estimate. That's how we assume that the data was generated. We assume that somebody is generating the data, and they are always following the behavior policy.
So that's where the first one actually Q-learning, right?
Yeah, in Q-learning we don't do that.
Yeah. So like Q-learning is not exactly a policy SARSA. In the sense that it could happen that you don't update because you sample something which is not the max.
Well, Q policy is expected SARSA, but like it's like one instance of expected SARSA, where the target policy is always the one which is greedy with respect to the current estimate. So in expected SARSA, what we do is we say, okay, or I will just go back to the slide. It will be better than if I am writing it by myself. So in expected SARSA, what we are doing is we say, okay, instead of sampling this action from the behavior policy, which is what normal SARSA does, we will explicitly compute the expectation with respect to the target policy. And so this works for any policy, but if this target policy is explicitly the greedy policy with respect to our estimates, we get Q-learning. But when you say it like that, I thanks for the comment, it means that if you are doing expected SARSA, you can get rid of one of the important sampling ratios, right? For expected SARSA, this can be T plus N minus 1, because the action in time step T plus N is not being selected by the behavior policy. Instead, we compute the expectation of the target policy. And this also shows why Q-learning actually needs no important sampling ratio, right? Because in one step, expected SARSA or Q-learning, these bounds are so that no action actually needs of policy correction, right? Because the AT is given and AT plus 1 is not needed by these algorithms. So we were lucky with expected SARSA and the Q-learning that we didn't actually use any action during the updates. But once you start doing two-step SARSAs, you cannot easily get rid of the important sampling ratio. So things will get more technical. So at this point, it took me several years to actually naturalize why it doesn't bother us that the AT was actually generated from the behavior policy. I say that it doesn't matter, and what we do is we do the update for QST AT depending on something, right? So yeah, there is no AT plus 1 there in the formula, but here in the formula, the AT is being used, and it was generated by the behavior policy. So why does this not matter? Well, it does not matter because the AT is already given to us. We compute the value estimate conditional on the ST and AT already there, right? So even if the target policy would not select AT, for example, it does not matter. We are just computing the estimates for this action. And the fact that that might not be chosen by the target policy doesn't matter. We have just computed something new or something not needed. But if you consider like this expectation, like how does the return look like, or how does the Q value looks like for this case, then here in this expectation, there is no AT, right? Because AT is given. So if we would look at the definition of the action value function, we would start by selecting ST plus 1 from the environment, and then AT plus 1 from the agent, and so on. But the AT is no longer a part of the estimate because we have put it to the conditional part. So it doesn't really matter. It might not be useful because the target policy might never want to get into the state. But other than that, the estimate is like the correct one. What would the target policy do if it started in this specific situation? Yup. So we can write this again as an algorithm. It's get larger and larger, as you can see, but the difference is that we would just add the important sampling ratios there for the actions which we have used to actually generate the rewards. So it's very similar to the n-step SARSA. We just need to include these corrections for all the actions which actually play a role in getting this n-step return. Yes?
The n-step return, like the GT means sum of rewards from the step t towards the end, and then like just like a
Yes.
of return.
Yes, exactly. So it's here in the slides. So this n-step return is the discounted sum of the first n rewards multiplied by the appropriate discounting. But then it computes the remaining, or it estimates the rest of the episode by looking at some value function. So the n step doesn't really matter. It doesn't mean that it's just the sum of the n reward. It means that we will estimate the whole episode by doing n explicit steps and then computing whatever estimate we have for the remaining part.
That's why we also compute the value function.
Yes, for being able to use, like in any temporal difference, we need value functions because in any temporal difference, we estimate returns by doing some number of steps and then looking up whatever estimate we have for giving us the value function in the state where we have got. Sometimes we have action value functions, so we estimate this from some Q, but generally we need to compute the value function for the state where we have got after the n steps. So we always need to keep it, but if we are having action value functions, we usually don't explicitly also keep the value functions, but we will do that later. So, yeah, this is correct in a sense that this should give us a return not from the beginning of the episode, but from the time step t. So when we say gt, so it's here. Like when we say gt, then we mean the return when we are like starting in this time step t. So the rt plus 1 will be there without a discount. Yeah, and so that's because even here in the first reward, we don't have gamma to t, right? This rt plus 1 is there multiplied by gamma to 0. So when the GT is not really multiplied by gamma 2t everywhere. You can see that we are actually taking it out explicitly. And it's just about definitions. So GT should be the return when we start in ST. So even if it has happened somewhere in the middle of the episode, the estimate itself just says, okay, let's consider this state, and let's see what we will get when we are in that state. So from that situation, the first reward which we get without discounting. If you consider the overall episode, some G0, then that would encounter GT in the future, so that would discount GT by gamma 2t. But when we define the return in that specific time step, then it doesn't know how long it has taken to get there. Right? That's because the environments are Markovian, so we don't care how long it took. The estimate is always from the point of the state where we are at that time. So that's why it doesn't need to be here, and that's also why it's not here, because it just means this is n steps into the future, not t plus n absolute time. So it is a bit like we have got these two views, right? The value estimates don't know about times, they just care about states. And then we have the episodes, and the episodes care about time because that's how they were generated. So the G is indexed by t, but the value functions are not, so it depends on circumstances whether we just forget the times or not, because there is no time t here, but there is time t here, because that's the only way which makes sense. But it's tricky because we have got these two different views and we need to switch them depending on what's happening. So I think it's time to take a break. No, we don't. Sorry, we have one more algorithm to go, and it will be better to do it, and then sweep it aside, and then start doing start working with the models, right? So one more algorithm. That will be the ultimate n-step off-policy algorithm. We don't, well, importance sampling is tricky, so we had Q-learning, and Q-learning was great because no rows were anywhere. So couldn't we come up with an algorithm which would be off-policy n-step and would include no rows? Well, because I'm asking like that, there is an obvious answer. It can be done somehow. So now I will show you how the algorithm looks like. The thing is, expected SARSA kind of did it for us, right? But the problem with expected SARSA is that while it can help us in the final estimation of the V as t plus n, right? There are some actions in the initial n steps which are sampled from the behavior policy, but we need them to be sampled from the target policy. So we need to use some similar trick by considering the target policy in every step of the n-step return, and it can be done. So let's have a look of how it will look like. So we know that this one-step return, that's what we have used in just the expected SARSA, looks like this. We get the reward, and then we estimate the value function in the resulting state by computing the expectation, right? By considering all possible actions from the target policy and using the Q value estimate to tell us how good they are. So now we need to do the similar thing also when we are doing the two-step return. So how we will do it? Well, we will get the reward at the beginning, that's the same thing. Then, in the t plus 1 time step, either we generated the a t plus 1, or we need to consider also the other actions, right? So let's go over all possible actions which we can go in the sample from the target policy. If we are considering an action which is different from the one which we actually took, right, then we want to know what would happen if in this state we did something which we did not do, in fact, something different. But, so if you imagine that we have got this one episode, right, then in this state we are interested in seeing what would happen if a different action was taken. We don't see this from the data itself, but we have an estimate which could tell us how good it is. Well, it's just the estimate in the state where we would, just the estimate of if we would done the action, right? So what we can say is, okay, so for the actions, not the one which we have actually taken, we will just use our Q-value estimate to tell us how good it would be if it would have happened. And then for this one action which we actually took, we can do better. We don't need to use the Q-value estimate immediately. That would be just a one-step method, right? Instead, because we are still on the track of the episode which we have simulated, we can just use the one-step return, like we can just estimate things from the data, right? So what needs to be here is the discounting. That's the same thing as here. Here is the probability of actually taking the AT plus 1 from the target policy. And here we will say, okay, recursively just do this, right? So consider, again, taking all the actions. If it is the one which, or if it is not the one which we actually took, just take the Q-value estimates immediately, and otherwise just go to the rest of the episode, right? So when we do the estimation here, we always consider what could happen. The non-taken actions, we can look them up in the Q-value estimates, and if we are keeping on the episode, we can just do it. So recursively like that, we can get an estimate where no action is sampled from the behavior policy. It was realistically, but we have a formula where we consider AT plus 1 to be generated with the correct distribution, so we don't need to fix it because we do not use the fact that it was generated by the behavior policy anywhere. Of course, this can generalize not just two-step but to n-step, but the formula is still the same, right? When we consider actions not taken, we estimate them using Q-value, and when it was taken, well, we will just look at how the remaining n-minus steps look like. So the algorithm is called n-step 3 backup algorithm, and in some sense, it seems like the best algorithm, right? Because it gives you of policy n-step, no weird rows there. It even works without knowing the behavior policy. We don't need to explicitly do the correction anywhere, so we don't care how the data were generated. We just get them and we can use them. So why is this not the best algorithm? Well, one problem with this algorithm is that it's not very statistically efficient in a sense that weird thing which is here is this multiplication by the target policy. If you would consider a usual n-step return, it would say RT plus 1 plus gamma times the return in the next step. But here, what we are doing is we are paying the price of multiplying things by the probability in the target policy. Even if we have taken it during the episode, we still need to discount it. So if this quantity is larger, smaller than 1, non-trivially, then we will not be able to learn efficiently from many samples because that's what we pay for having the off-policy algorithm. So we will see improved version of that in 7 lectures or something, which will be able to deal with this somehow, and that would be something which is actually being used a lot nowadays. But right now, this is the best thing which we can do. So you only want to use this when you actually are doing off policy, because doing n step on policy algorithm would be more efficient, because we will learn more from the future, or from the actual experience with the environment. So, small break. Let's have a look at where we stand. Until now, all our value function estimates and the action value function estimates were being computed as a table for some number of fixed number of states and the fixed number of actions. And we estimate each of these values independently, so we don't share anything either across states or actions, which means that it's not as efficient as one could hope for. And we usually estimate the action value function, so the Q, so that we don't need to have the model of the environment. So that's called a model-free method in the sense that we don't know what the model is. If we had the model of the environment, it would be better to estimate the value functions, because there is less of them, and then choose the action by looking what would happen if we have taken the action and computing the value function of the next state, and this is the place where the model is needed to tell us what next state we would get into if we started in S ended A. And we have seen various flavors of the algorithms. In Monte Carlo, we estimated return by going through the whole episodes. In temporal difference, we only considered some number of rewards, and then we have used our estimates to estimate the return from the rest of the episode. The algorithms can use either the same policy to generate the episodes and as the target of the value function they try to estimate or not. And I said the of policy are more general, but slightly more complex to deal with. So now let's put the neural models somewhere. So, temperature warning. It's getting hot in here. We are getting to the part where things will be interesting. I hope it will get away. So, we will now, instead of having a table, right, we will have a model which will do the estimation of V or Q. So we will assume that we have some model, usually neural network, which will give us an approximation of the value function with some parameters. So unlike deep learning, usually the W's are being used, so the parameters here again are going to be W's, and we can have that either for the value function or for the action value function. But the way the parameters, they will influence not just one state, but probably the output for many states. So when we update our estimates, or when we train our models, we need to say which of the states are the one which we care about, right? Because if you imagine that we have got a value function estimate which can get a lot of states, and then we will say, okay, in this state produce this output, in this state produce that output, in this state produce that output. Then when training on these quantities, the model will also differ on some other states. Like we cannot just effectively change the model to say, in this one specific state S, generate exactly this output, because if we try, or if we train it to do that, it will change the estimate in all the other states as well, because they are interconnected with the parameters. So when we are training our models, we will need some objective which will also include the information of which states we actually care about, right? It can happen that when we have an episode, I don't know, in some of the environments, in the carpool, for example, then some of the states might be much more visited than other ones. So we want this to be reflected in our approximation to say, okay, so in these states, let's make a smaller error because we are visiting them frequently, while in a state which we visited just once 2 hours ago because the driver of the cart was drunk and crashed or something, then we probably don't want to take it into account too much when training the model. So we will assume that we have a state distribution, some state distribution, and when we are training the model, we will minimize the mean square error between the real value and our estimate, but weighted by this state distribution. So this is called mean squared value error, denoted as this VE with the top hat. And that's the usual function which we will use because we don't want just to use the usual mean square error, because that would mean that even a very infrequent state would influence, like the error in a very non-frequent state would have the same weight as an error in the state which we visit a lot. So to consider what these distributions are, well, for on-policy algorithms, this is quite a straightforwardly the on-policy distribution. So the on-policy distribution tells you how often you are in the state S. So the fraction of time you spend in that one specific state. When you follow the policy, right? Because in this on-policy settings, if you simulate a lot of episodes, you will see which states you visit often. And that will be the ones where you will want your errors to be minimized. Right? So how to get this on-policy distribution? So for episodic tasks, we can explicitly define how it looks like. So if we have a distribution of probabilities of our initial state, right? So if HS tells you what's the probability that an episode starts in that state. And then if you had the number of times you spent in some given state, right? Then how we could compute it? We could say, okay, so the average number we spend there is that we either start there or we were in some state as prime, some other state, which happens with this number of times, and then we will actually get to S, right? So the number of times spent in S is either we start there or we are in some other state and transfer to that one when doing the action from the policy from the agent. So that's what I mean when I say on-policy distribution. And when I want it to be a distribution, I could take these counts, like the average number of times where you visit the state S in an episode, and normalize it. Right? That's why we are saying for episodic tasks, because, well, this denominator needs to be finite for this to work. For infinite episodes, it's difficult to even talk about on-policy distribution. So if this is like limited horizon task, then it's straightforward. If it is really just episodic, then we will need discounting to make sure that all the counts are finite. So how to deal with discounting? So we will now see a trick which we will use in future. Now, when you have the discounting, non-trivial discounting, we can actually instead modify the original MDP to do the discounting inside, and then we don't need to handle it explicitly. So in some sense, it was superficial to say we will get explicit discounting, because we could have, like for every discounting factor, we actually can update the environment so that whatever we do without explicit discounting in this new environment is exactly what we did in the original discounted environment. So how does it work? Well, imagine that we have got this terminating state, and in every timestamp, what we will do is we will either stay there in the original MDP, or we will say, and now we'll stop. Right? So with probability of 1 minus gamma, right, we will say, okay, end of episode, right? And of course, with probability of gamma, we are just continuing. So in the discounting, what we did is we said, okay, everything in next step, I don't know, is this multiplied by gamma, but instead you can imagine this gamma to be part of the dynamics of the environment of the thing which tells you where you'll get. And well, you will get to the next state only with this probability of gamma, while with 1 minus gamma you will just stop. So we can do this actually, and this also shows that having different gamma changes a different optimal policy, changes optimal policy. Right? When you change gamma, you change the environment practically, so the behavior might be different. So that's why gamma is tricky, because when you use more aggressive discounting, then you will concentrate more on the near future, so your optimal policies might be different. I could have told you this at the beginning, but there are so many things to be said that I have left it for now. For continuing tasks, we require the gamma to be smaller than 1. We can use the same definition, even if now the interpretation, well, it is still nearly the same. But we need to have the discounting there all the time, otherwise it wouldn't work. There are some papers which show that this actually makes very little sense. So even the authors from the original book or something are saying that, well, we don't really think that in the continuing case the discounting is a good idea, and then they are trying to develop a theory to handle that. Well, the good thing is we will not be really working with continuous tasks much, so we'll just ignore this kind of problem, which is now hanging over all the reinforcement learning, but because nobody's using this continuing tasks much, and it's more like a theoretical stuff, people don't care much. So, how are we going to train our models? How are we going to do the updates of our value functions? So we know that imagine that we are generating an episode in an on-policy setting. So we have got states, actions, rewards, and so on. States, actions, rewards. So the loss which we want to minimize is, well, if S comes from the on-policy distribution, right, minimize the mean square error. So what I have done now is that here in this mean squared value error, this was summed over states, but with respect to how they come from the state distribution. So this is like the expectation where the states comes from the distribution. And if we are using the on-policy distribution, then this just says, okay, from the states which we get when we follow the policy, right? That if we use this one specific distribution, and we'll use it most of the time, then this is not really bad. It just says the states which we care about are not the one which are all possible states, but the one which we actually encounter when we follow the policy. So if you imagine that we are generating the episodes like that, then we don't need to do that, to handle that, because if our loss should be an expectation where the states come from the on-policy distribution, well, that's exactly how we generate our data, right? It comes from the on-policy distribution because, well, they are generated by following the policy. So even if it seemed weird that I started talking about that, in some sense, it will make the algorithms as simple as possible because, well, we will just be generating data, and in every state, we will just do the update in that state. So the states visited often will get more updates, and that corresponds to them being more important to us, right? So even if we know what these on-policy distributions are, in many algorithms, it will just go away because we generate our states exactly that way. So if we do that, what we need to do is we just need to minimize the mean square error. So here we have the true value and our prediction. So the gradient of that, right, what it is. Well, the gradient of a square is 2 times the value inside the mean square error, and then the gradient of the value function itself. So when you look at it, this is not very different from what we did until now, because we will say, okay, so the update of the parameters looks at the difference between the value function estimate, and we estimate this by some return, minus our current estimate. So that's exactly what we had there previously, right? GT minus QN, or I don't know, G minus QN to be safe. But then, of course, we also need to compute the derivative of the value function approximation itself. So the Monte Carlo or temporal difference methods are still here in the same way because we estimate this return as we did before. It's just that we are updating a slightly different set of parameters. Instead of explicitly updating our estimates, we are updating the parameters which we use to compute it. Right? So if we try to estimate a value function of a given policy, we would generate the episode, and then for every step, we will update the parameters by looking at the difference between the return and our value function estimate times the gradient of that. But when you implement it, you really say mean square error between the estimated return and whatever the model does. That gives you this formula automatically. So on the slides, they do it like that. But if you imagine implementing it, you would really just say Keras losses mean square error. Or maybe I should go for PyTorch, right? So torch, I don't know what, mean square error, which will just do these updates. Yep. So let's consider a very, very simple model, which would be some linear approximation, or some linear method. So let's say that our model works by having some parameters which are multiplied by some suitable state representation. Right? So we have got states, we will represent them using some vectors, like some features, and for each feature, we have a weight. So the model is just a linear regression, which multiplies the ith feature with the ith weight. Yeah. So what exactly does the SGD rule says? Well, here, there should have been the gradient of the value function with respect to W. Well, that's the gradient of this with respect to W, which is just XS. So that's just the features of the state S. So if you look at it and you imagine that this XS would be one hot representation, so every state would get their own weight, then this is exactly the tabular method which we have seen so far, right? But it makes sense. In the tabular method, what our model did was for each state, we could have generated any number independently on the others. So if we represent the states with one hot distributions, we have got as many parameters as there are states, and the output of the model, well, for the state S, it's exactly one of the parameters which gives you the value for S. So they are independent. So there is no reason why these things should be different, right? We can get tabular methods by representing each state with one parameter in our neural network. And then the update of these weights, well, this thing would say, ignore all the weights apart from the one which corresponds to this state. So even if this update seems to be updating all of the parameters, most of them, actually all of them apart one, are going to be unchanged. Only the one parameter corresponding to the state in question would change. So previously we said VST is something, right? So this will happen by this one hot distribution, and then this formula is exactly the one which we have used until now. right? So we know that originally it was motivated by computing the average of all the observed returns. Now it's motivated by minimizing the mean square value error, but they are the same thing actually. Right? It's nice. We are now connecting it to everything. So how we can generate the states? So we can, the easiest thing how to generate a state representation is just to do bucketing, right? Formally, it's going to be called state aggregation. So let's say that we have got 1,000 states from 1 to 1,000, and we will have a uniform random walk where the transition can lead uniformly to any of the 100 neighboring states to the left or to the right. So when we represent the value function, we could say, okay, we have got 1,000 numbers, so let's just group them into groups of 100 states, right? So we will have 10 parameters, right? One for each of these groups. So this is something which we have done implicitly in the assignments, right? I discretized the states for you by saying, okay, all the states in this range will be represented by this one discrete state. So that's the same thing we are doing here, right? We will represent all those states, for example, in this range using a single value, because in our model there will be just one parameter which will be used for all the values in this range. If we do the Monte Carlo policy evaluation, then we will get this blue curve. The red is the correct one. Yeah, the thing is we care about the probability that we'll get to the right. Right, so that will be mostly 1 on the right, minus 1 on the left. Okay, so it's not probability, it's plus 1 there and minus 1 there, sorry about that. So the true value is like a linear function, and then the approximation is this staircase function. The interesting thing to see is, for example, here, one would expect maybe that the blue part should be split into middle by the red one, right? It will be the average of the true there. But the thing is, it's a weighted average according to the state distribution, right? Because we visit these states more often, they play a higher role in computing the average. So this blue line, this one, right? That's just the weighted average of all these values multiplied by the state distribution. But generally, it does a reasonable thing. Okay, so if we would use linear method, what we could do, well, there are many methods which people have played with in the past decade. We could do some polynomials, we could do some Fourier basis, radial basis functions, and so on. But of course, nowadays, we don't care about manually constructing features for models. We have neural networks which construct feature for us, right? So for many assignments, we will just say, yeah, well, we start with these images, then we'll stack 3 convolutional layers, and they will magically compute everything for us. I just want to mention one specific construction, and that's the tile coding, which is somehow interesting and useful and can create quite fast algorithms. So imagine that I have got like a 2-dimensional space, and I would like to represent a point to be represented. So in the feature aggregation, you would just use whatever tile where this point belongs to. That's exactly what's happening in the car pole and mountain car in the assignments, right? I'm doing this kind of bucketing where if I'm in the 4-dimensional space, I just tell you which hypercube you are in. But a way how to do it, and the problematic part, of course, is that when you move slightly but change a tile, the behavior of your algorithm can be quite different. So there are these discrete changes there, and we can improve the situation by using the so-called tile coding, where in the tile coding, we will not use just one grid, but we will use several. So on this image, there are 4 grids of square parts, which are offsetted with each other slightly, right? So when you have a point, it belongs to one tile in all these planes. So instead of one hot features, as they are here, we will get 4 hot features in a sense that the value of one state will be a sum of 4 parameters which corresponds to tiles on the different planes. And the good thing is that if you move to the left, for example, then you will hit a boundary of the first tiling of one of these. So after you will cross it, your behavior will, well, 3 tiles will be the same as before, and just 1 tile will differ, right? So this allows you to make more gradual changes in the behavior, not just, okay, I am now in a different tile, so I behave completely differently. It's just my behavior is generated from components, and now one of the components has changed, but all the other stay. During training, when you are training such a model, normally you update 1 parameter when you do the training, but now, for example, in the 4-tile encoding, you will have 4 parameters. Each of them will be updated, which means that in some sense, we effectively learn 4 times as fast as before. So the usual practice is to normalize the learning rate as well, so that the effect of the number of tilings is not really visible on that too much. So this just all means if you are using several of the tiles, don't worry that the learning rates are much smaller. That's to be expected. Yep. So in the random walk example, this one, right, what we can do is we could try to see what the difference would be between the state aggregation, so just this one set of tiles, or the tile coding with 50 tilings. And well, as you would expect, it gets better and better because you can represent these states more accurate, so what you would have expected, right? Uh-huh. Yeah, so the question is, what is the difference between one dense tiling and then several much coarse tilings overlapped on each other? So the difference is that now the states are not completely independent. In this dense tiling, when you want to learn something about this tile, you do it only when you actually see it in the data, and even if you have a good estimate for it, you need to be able to, so it just gives you information about this one small tile. So the more dense you have one tiling, the more data you need to collect to cover all of these parts because they are independent on each other. While here, we share some information between the states, so we don't theoretically necessarily need so much data to get a good estimate, because whenever we see a point, we actually update several parameters. So there will be some trade-off between the density and the number of tiles, and also the trade-off is in the time, right? Because here, everything is one hot, so you get the estimate in constant time, you do the update in constant time. Here, computing the estimate and doing the update takes time linear in the number of tilings, so that also plays a role there. But the usual practice is to go with dozens, larger units or small tens of tile codings, and that seems to work kind of fine. Like you can consider the tile codings to be like on the boundary between one hot encoding, like the one hot encoding, that's just the tabular method which we had, and on the other hand, like a full neural network here, where each state and each parameter are all connected. So here you have got the tile encoding where you could represent each state with a small fixed number of weight. So even if you have got thousands of states, you can still do the inference and prediction in kind of small time. And there are situations where this works kind of fine and much more efficiently than the neural networks. So that's why I'm talking about it, and we'll do an assignment to see that it actually is is interesting and it does something good for us. So one last remark is that when you construct these, you have to be kind of clever because if you have several dimensions where you even if you are just in the 2 dimensions, if you constructed the tiles by going the same difference in the x and y axis, right? So like this one, and also like on this image, right? Then it's not a good idea, because if you then look for one point, what are the tiles which intersect with that? It's kind of regular, right, in a sense that for some points, this is computed from tiles which are in this direction. For some other points, this is computed from tiles which are somewhere systematically around. So this creates some kind of systematic problem. So you want the offsets to be kind of independent, so that hopefully each point will be represented by tiles nicely distributed around it. I'm just saying this to you, but I will be doing the tile encoding for you. You won't need to compute which tiles you are in. I will do that in the environments for you, and you will be able to see in the wrappers code how it's done. And I do it correctly there. I'm just saying that if you also constructed the tiles manually, it just needs to be slightly reasonably. Okay, that brings us to the end of today's lecture. So I covered 41 slides out of 63. I was optimistic. Well, I knew we will not make everything. So thank you very much for your attention. I know that no convolution layers yet, but hopefully the neural networks will come very soon. Tomorrow is the consultation if you want to ask just before the deadlines for the assignments. And otherwise, have a nice week and see you on Wednesday.